Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about reality checking a hydrodynamic model of a floating system, like a ship, when you're working with load RAO data. Now, we've got a similar video on working with motion RAO data, but working with load RAO data is a little bit different. And again, re-emphasizing, why would you want to do this? Ship motion prediction models can be used in very complicated scenarios like mooring analysis or marine operations analysis. And these layers of complexity you keep adding really pays to look for ways to check that the model is set up correctly as you go along. Because if you're looking at final results and trying to figure out like something just doesn't look right, it takes a long time to untangle everything and figure out what's wrong. So load RAO data is a little bit different. We're going to be talking about forces in ship motion prediction tools like the ProteusDS ShipMo3D toolset. It calculates wave radiation and diffraction and excitation loads, and these forces are what we want to incorporate in another model, and not the resulting motions. And using that information it's treated a little bit differently, and we can do different kinds of reality checks with it. But some of the similar ideas still apply. And though we're going to be talking about ProteusDS today, a lot of these ideas are going to apply to whatever kind of ship motion prediction tool you're working with. So we're going to be working with this 80-meter generic trimaran project. It's just something I was working on recently and thought it would be fun to work with. It's not a real vessel, it's not a real project, but it also doesn't really matter what you're working with, whether it's a barge or a monohull or trimaran or whatever. A lot of these ideas will also apply to what you can do. So in the ProteusDS ShipMo3D toolset, what you're going to be doing, there's lots of other tutorials showing how to use this and how to generate the radiation and diffraction loads. In the build ship application, at the very bottom, you'll see export ProteusDS radiation and diffraction terms. So when you run that, you'll see this file come up, ProteusDS radco. Now our file name prefix for the project is trimaran, so that's showing up here, ProteusDS radco. There's a little README file that kind of helps a little bit, but the radco file is the one that we want in here. So what I'm going to do, first things first, is we'll make a brand new ProteusDS Simulation Toolbox project. And there's our empty world, little pre-visualizer window. I like having the water surface here. We'll make a new rigid body, 80 meters load RAO. Create that rigid body. Okay. And we want to save this project as well. We'll call this load RAO trimaran. Okay, we got our little folder showing up here. So I'm going to copy this radco file. I also want to use a visualization mesh. We might use this custom mesh for more complicated calculation of forces on the ship as well. So we've got our project. First, let's add the visualization model here. 80-meter hull. There's the feature name. Go to feature definition. It's not in the parts in the library, so we have to add it. And I'm just going to copy and paste the file name here. So this, as a visualization feature, it's purely for just showing what the rigid body system looks like. As it happens, I've used this for the hydrodynamic calculations. There is a reference frame difference in orientation between the ShipMo3D toolset and Proteus, so a 180-degree roll solves that. The draft at midships is 3 meters. By default, we've got everything kind of set up and configured the way we've drawn the mesh, and with the rigid body reference frame at aft and baseline, this makes it really easy to kind of make a mapping of how everything is set up. So we have a 3-meter position that will get us our 3-meter draft of the vessel there. Excuse me. So now we want to add the hydrodynamic database, as we call it. Call it RADDIF hydrodynamic model. If you aren't sure for the names of these, you also have this context menu, insert hydrodynamic features, RADDIF hydrodynamic model. Trimaran 80 meters HDDB. And we're going to go to feature definition. Now we have quite a few more options here compared to the motion RAO. And that's because you can turn on and off different sources of loading. Now, load RAO is sort of, this term is used by some people. Some people use a different term for the loads. The general idea is that a lot of the loads are driven by, well, we have these waves present in our simulation, and then there's a direct mapping to the wave excitation force on the hull, to the diffraction force on the hull. Oftentimes you'll find in ProteusDS we call it hydrodynamic database, and the reason for that is that there's more in here than the diffraction radiation loads. We have resistance loading, extra stiffness and damping that you can add, restoring force loading, radiation loading, and all that kind of stuff. And then these flags turn it on and off the different sources of loading. Hence, we sort of use this more generic term, hydrodynamic database, but the idea is still kind of similar. Okay, so we have a visualization feature. We've got this set up here, and other things that we need to do. We definitely need to set the inertia values and the mass values. So what I will do is we can take these straight out of our ShipMo3D project. So when we set the displacement and import the mesh in panel hull, at the very first step in ShipMo3D, what ShipMo3D will do is say, oh, well, given this displacement and footprint in the water and the hull shape, this is the total displacement. So I'm just looking at the output. It's pretty close to the top, and it says, well, the mass in a static condition has got to be equal to this, so I'm going to just copy and paste that straight over here. And then we have the inertia values. Now, you do need to know these, and you do put them in build ship. These are just rough estimates. They're not meant to be carved in stone or meaningful or representative of a real trimaran, but it's what we got now. So for the roll radius of gyration, that's going to correspond to 7 squared times our mass is 67 e to the 6. And then we've got a radius of gyration of 20 for pitch and roll. Sorry, pitch and yaw times our mass gives us 552 e to the 6. Okay. And then in terms of our CG position, well, we set the Z position, so that's -5 because we have a positive Z down, and then we need to know where the CG position is. Now, you can get this from panel hull as well. Distance from front perpendicular to X origin at the longitudinal CG. So we have 80 meters minus 46.848 to get the distance from aft forward is 33.1. Okay. Now we have to determine how we want to set this feature up. Actually, if we go and look, this is a much easier way of doing things. If we open up the load RAO, well, that's not right. The RADCO value here. We have CL position from waterline, CL position from baseline. This is the center of loading position that the ShipMo3D toolset is saving and referencing everything with respects to, and it turns out that ShipMo3D saves all the hydrodynamic information with regards to a reference frame where it thinks the center of gravity is. So we can also just use these values, and it turns out they're exactly the same here. Now, different from the motion RAO, this ProteusDS will use this location internally and apply that, so we don't need to move the feature anywhere. It's just automatic. So now, first thing we can do is just a calm water test. We've got a plain simulation here. There's no waves turned on. Let's just see what happens now. Now it runs pretty fast because there's not a lot going on. There's not a lot of waves, and it's just one single rigid body. We haven't done anything. We're not doing a decay test or anything like that. I just want to take a quick look at it and make sure it's sitting flat in the water like we expect. If we see it moving around, then something is wrong and something is off. So I'll play the simulation, and it looks like nothing's happening, which is perfect. That's what we hope to see. Great. Okay. So that's the first reality check, just doing a calm water test. If you've got reference frames in the wrong location or the CG location is off, then it starts to trim, or it might turn sideways, or something else might go wrong. So the next reality check that you can do is a decay test. Now, one thing we can do here is just move it up a little bit in the water. You don't have to go crazy, but we'll just do a little heave decay test. So we'll run this, and we expect to see some heave decay happening. And there's some wave radiation here. Multi-hulls actually don't have incredible heave radiation in some circumstances. It sort of depends. But it doesn't look like it's that much different, but I only moved it a meter. Oh, sorry. I got to reload the data. So we use this button to reload the new simulation data. You don't have to do it this way. It's just a little bit faster. There we go. That looks a little bit better. It's off by a meter, and we should see it oscillate and heave. And it's, you know, more than 1,000-ton vessel, so it's going to have a kind of low wave period here. Remember, there's plotting. You can right-click here and look at positions, Z versus time, and you see some decay happening and some oscillations there. This kind of gets to what I was talking about, you know, wave radiation for. It's not incredibly potent for multi-hulls necessarily, but there you go. Other things you can do as well is like roll decay or pitch decay. So we'll set this back to 3. Maybe we'll do a little bit of a pitch decay test. And we'll do 5 degrees. Now pitch is going to be set based on the rigid body frame location of the back, so that might bring the bow quite a bit out of the water. Let's just move that back down to maybe 2 and run a little simulation here. And if you close the post PDS window, no big deal. It's pretty quick to bring it back open again. Okay, we'll reload this result. So we're not doing heave decay now. We're looking at pitch decay. So you can see the bow is kind of not out of the water, but it's just doing that. There's going to be a little bit of coupled heave motion here as well, but we're just basically seeing the thing kind of calm down a little bit. That's looking like kind of expected, so that's good. Okay, so we've done first check was calm water check. Second one was a bit of a decay test, and the third check, similar to what we were doing with the motion RAO, is looking at a low frequency wave, or in other words, long period wave motion. And in those conditions, we want to see the vessel following the sea surface. So I think we were using something like 15 meters, 25 seconds. Let's set up a head sea condition. Why is that a head sea condition? Well, we've got a ship heading of 0. It's pointing north. You can see by the compass here. And then the wave heading is 180 degrees, so it's going from north to the south. That makes a head sea condition. And we'll run it. Wait. One thing. Well, you know, let's see what happens here. I didn't turn on any wave ramping. The problem with not having wave ramping on, as we'll see, is it instantly, the vessel might instantly be sitting in a wave trough or something like that. Yeah, so it's in the air. This is going to cause a lot of transient motions as a result. I mean, that's kind of fun to play around with, obviously. We'll see it eventually calming down, but that's a distraction from what we really want to be doing here and just checking and seeing what happens. So I also see that I left the initial pitch on, so we'll set that to 0. And if we go to the environment, what we have here is environment transition mode is actually already on. We have a 0 wave ramp duration. So we'll set a 10-second, and that's very short, but it's better than plopping the ship in the ocean. So what's going to happen is the waves are going to ramp up over 10 seconds, and there will be some transients from this, but and maybe we need to run a longer simulation, but Let's just see what happens. Okay, so we're starting off flat, as you can see here, and the waves are going to come from the, they should be coming from the right to the left as they go in a southerly condition. And that seems to be gentle enough to not cause too many crazy transients. This is really nice here now. I've got pretty big waves here, but like it's helping me to visually see. It's got a nice consistent displacement. The heave motion is following the water surface. You know, the pitch is going down the back of the wave. The pitch is going up as the wave's coming, so it's following the wave slope. It's following the water elevation. This is starting to give me a lot of confidence that this is looking good and like how I would expect. Similar to the motion RAO check, you could look at something in beam waves to look at roll and make sure that's good. I think what we'll do is we will, again, as we mentioned in the motion RAO check, it's worth doing sort of a shorter wave period just to sort of make sure there's nothing really odd going on. Now, we don't have something quantitative like, oh, the motion RAO should be this much. It's going to be totally different for every ship and circumstance. But, you know, you can see for something that seems really weird, like if the bow is coming way out of the water or something just doesn't look quite right. So we use 2 meter, 8 seconds in the motion RAO check. This is pretty steep, but it's more representative of maybe a coastal kind of wind-driven kind of wave system. And what we kind of want to see is, again, you know, something that's looking reasonable. We're not seeing parts of the hull flying out of the water or anything like that. And that's looking pretty good. We're not seeing any, I mean, again, it's a long and skinny ship. These are much shorter waves. There's not a lot of bow flare or anything like that. So, you know, we're getting a little close to some green water on the deck, but that's all right for this condition. Yeah, so 3 reality checks that you can do, making sure when you're looking at something like a more complicated scenario. In, for example, Simulation Toolbox, we looked at the calm water test, we looked at a decay test, and we looked at a long period wave or low frequency wave condition where we expect to be following the surface, and we did a little reality check here to make sure that at a sort of like wind-driven wave period to make sure that things are looking copacetic. So now I would move forward with confidence, adding things like you know, a towed array or mooring system, or you know, using this model setup in a more complicated scenario. All right, thanks for watching.